Hello, my dear students and the rest of the learners. Welcome to part 4 of 8 in the series of Fundamentals of Developing Computer Program, in which we are going to learn about program design and analysis. My name is Meme JM, or you can simply call me Emily Swap. In this presentation, we are going to look at the introduction to program design and analysis, the procedure for designing a program, the program design approaches, the program design or development tools, and the factors that can affect computer program design and analysis. And lastly, we are going to look at software design levels. Let's begin by looking at the introduction. Program design is the process of developing the program's processing or solving logic or algorithm to enable the programmer come up with the models of the expected program, showing the flow of events and data throughout the entire program from the time the data is input to the time the program gives out the expected information. An algorithm is therefore the series of steps to be followed in solving a problem and in the execution of a program. The algorithm is developed through the following steps. Number 1, the problem has to be understood by the programmer. Number 2, the expected output has to be identified. Number 3, the logic that will produce the required output from the input has to be developed. Number 4, the algorithm should be tested for accuracy for a given set of input data. Number 5, the steps are repeated until the desired result is produced. So what is the procedure for designing a program? The 3 fundamental steps for designing a program are: number 1, you need to define the output and the data flows. You need to have a clear idea of what the program should produce as output and what data is to be input to produce that output. The programmer should know what every screen in the program should look like and what will be on every page of every printed report. Number 2 is to develop the logic. Here, you think of how you will make the computer produce the desired output from the input made after you and the user have agreed on the goals and output of the program. You thus develop the algorithm for the program using any of the available program design tools, such as pseudocode, or using pictorial representations, such as flowcharts, etc. Number 3 is to write the code. Here, you transform the algorithm designed into an actual source code using a programming language that is appropriate in solving the problem at hand. You now translate the design into a set of instructions that can be understood and executed by the computer. Program design is therefore the actual development of the program's processing or problem-solving logic on the algorithm that enables the programmer to come up with models of the expected program. So, what program design approaches are used by programmers? A program design approach is a way to plan how to structure a program, what resources are needed, and how the program will be implemented. A successful program design approach follows a clear sequence of steps, building on each previous step. A programmer can thus make use of any of the following program design approaches: 1, top-down; 2, bottom-up; 3, data-driven. What is top-down approach? This is a design whereby, or this is a design which is also called divide and conquer. When using this approach, you first list the major steps or sub-problems that need to be solved. Then you solve the original problem by solving each of its sub-problems. Then, once you know the sub-problems, you deal with each one individually. During this process, you may need to break down each subproblem in a more detailed list of steps through a process that we call stepwise refinement. Therefore, you start by implementing the most general rules and work towards implementing those that provide specific functionality. In the top-down model, an overview of the program is formulated without going into detail for any part of it. Each part of it is then refined into more details, defining it in yet more details until the entire specification is detailed enough to validate the model. What about the bottom-up design model? In bottom-up design model, individual parts of the program are specified in detail. The parts are linked to form larger components, which are in turn linked until a complete program is formed. It implements the modules that provide specific functionality first, and then integrates them by implementing the more general modules. The third approach is called data-driven approach. One clearly distinguishes code from the data structures on which it acts and designs both so that one can make changes to the logic of the program by editing not the code, but the data structure. Here, the data is not merely the state of some object, but it defines the control flow of the program, with the primary concern being to write as little fixed code as possible. A detailed design must define the following. Number one is data structures. Defining the format, or this is defining the format and type of data the program will use. Number two is user interface. The design of the screen the user will see and how to enter data or display data. Number three is inputs. Here, you define the kind of data to enter in the program. Number four is outputs. The results or the possible data displayed from the system. Number five is algorithms. These are the methods for calculating outputs depending on the inputs. So, what are the key program design or development tools, or what are they? The program design normally involves developing the method of solving the problem by planning and creating a solution using program design or program development tools such as pseudocode, flowchart, data flow diagrams, structure charts, decision tables, and decision trees. What is a pseudocode? A pseudocode is a sequence of English-like statements that indicate the specific processing steps and the actions to be taken to solve a particular problem. These statements must be very brief and clear, indicating the title, starting point, the output, input, processing statements, and the stopping point. The process logic in pseudocode is expressed as a combination of sequence of events, decisions that need to be implemented, and actions that they may have be repeated. Some of the ones used in pseudocode may be drawn from a certain programming language and then mixed with the English to form structured statements that are easily understood by non-programmers and also make a lot of sense to programmers. However, the pseudocodes are not executable by a computer. Some guidelines to adhere to when designing a good pseudocode are: number one, always make use of short, brief, and readable statements. Number two, ensure that the statements are not ambiguous. Number three, outline and indent the lines clearly. Number four, show clearly the start and the stop of the executable statements and the control structures. Number five, state clear the input, output, and the processing statements using keywords that may be close to those that you'll be using during coding, such as print, read, input, etc. The following is an example to demonstrate how to write a pseudocode. This pseudocode is for calculating either area or perimeter of a circle based on value entered. Remember, every pseudocode must have its title, or every algorithm must have its title. So we normally have the start, and then in this case, our first activity will be to declare and initialize pi 3.143. Then we are going to prompt the user to enter value of radius. From there, we are going to check whether the radius entered is greater than 5. For 6, if radius is not greater than 5, set perimeter as 2 times pi times radius. Else, set area as pi times radius. Then display the computed results, and you stop. So this is an example of an algorithm. Let's now look at flowcharts. What is a flowchart? A flowchart is a pictorial representation of a stepwise solution to a problem by using special symbols that have specific meaning and short statements. It helps the programmer in developing the program logic and serves as documentation for future reference. A program flowchart is thus used to describe the flow of data through a particular computer program, showing the exact sequence of operations to be performed by that program in order to process data. It graphically represents the types of instructions contained in a computer program, as well as their sequence and logic. Flowcharts are used by programmers in two main ways. Number one, to plan the structure of a program before it is written. Number two, to describe the structure of a program after it has been written. Unlike a pseudocode, which expresses ideas in the form of short statements, a flowchart does the same, using both statements and special symbols that have special meaning. The process of drawing a flowchart is called flowcharting. Some of the special symbols used in programming, or some of the special symbols used in drawing a flowchart are as follows. The first symbol is this one. It is called a start or end. Of course, it's an ellipse. What is its function? Its function is to represent the start or the end point of processing. It is also called the ellipse or terminator. It denotes the beginning and the end of the program's algorithm. And therefore, my dear students and the rest of the learners, in the time you are drawing a flowchart, it has to include the start and the end. The other symbol is the flow control. It is a connector that shows a relationship between representative shapes. It also indicates the direction of flow or program logic. Another symbol is this symbol, which you call the input-output symbol. It's a parallelogram that represents input or output. It is used to denote an input or output question. The other type of symbol is a process symbol. It is a rectangle that represents a process. It indicates that a processing activity or data transformation is taking place. The other symbol is the decision symbol. It is also called a diamond or rhombus shape. It indicates a decision. It shows where a decision or a test is to be made between two alternatives. It is then used to specify a condition. Another symbol is the connector. Connector is used as a connecting point or interface for allowing or for arrows coming from different directions. The following are some basic rules or guidelines when you are doing a flowchart. Number one, each flowchart should have a title. Number two, a flowchart must have a start and an end. Number three, it should have only one entry or starting point and one exit point. That is, ensure that the flowchart has a logical start and finish. It should be clear, neat, and easy to follow. Number 5, the logical flow should be clearly shown using arrows. Number 6, use the correct symbol at each stage in the flowchart. Number 7, make comparison statements simple or instructions simple that is capable of yes or no answers. Number 8, avoid overlapping or crossing lines used to show the flow of logic, as this can create confusion in the flowchart. The lines should ideally be vertical or horizontal. The flowchart should not be open to more than one interpretation. Where necessary, use connectors to reduce the number of flow lines. Ensure that the flowchart is logically correct and complete. It also ensures that simple ones are used that can be easily understood by other programmers. There should be a list of activities inside each symbol. The following is thus an algorithm for solving our problem for computing either area or perimeter of a circle based on the size of radius using a flowchart. This flowchart contains an algorithm for solving our problem for computing either perimeter or area of a circle based on the size of radius using a flowchart. So this is the flowchart. It begins in the beginning. Then the programmer declares or sets aside a memory location to hold the value 3.143. And then the user is prompted for radius and he or she keys in a value. That value is read. It is then compared with 5. The comparison is meant to find out whether the value entered is more than 5. If the value entered is more than 5, the computer or the compiler will proceed and compute the area of the circle and display area. But if radius is less than 5, then the program will calculate the perimeter of the circle using 2 times pi times radius, and then it will display the results or output the results, and that will be the end of that program. Let's now look at the structure charts. Let's look at the structure charts. This chart shows the breakdown of a system to its lowest manageable levels. It identifies a program as a system with many components interacting with each other. It shows the overall framework of the program in terms of a hierarchy of modules, with each level showing progressively more detail. The main program is thus broken down into modules, and then modules are broken down into submodules, with each module performing a simple function. Modules are thus developed, starting from the top and moving down the hierarchy. This method ensures that all modules link in together as the program develops. The structure chart is used to show the relationships between program modules and generally depicts the breakdown of modules. The following is therefore an example of the design of the program for computing area or the perimeter of a circle based on the size of radius entered. So it begins with tabulating area or a perimeter. Then the entry for radius is done. Then the value entered is checked, whether it is less than 5 or greater than 5. If it's greater than 5, then perimeter is computed. If it's less than 5, area is computed. And finally, the results are displayed. Number 4 is what we call the decision tables. A decision table represents conditions and the respective actions to be taken to address them in a structured tabular format. It is a powerful tool to debug errors. It helps group similar information into a single table. And then by combining tables, it delivers easy and convenient decision making. They associate conditions with actions to perform. A decision table has 4 quadrants, which are the condition alternatives, the actions, and the action points. Each decision corresponds to a variable, relation, or a predictable or predicate whose possible values are listed among the condition alternatives. I repeat, Each decision corresponds to a variable, a relation, or a predicate whose possible values are listed among the condition alternatives. Each action is a procedural operation to perform, and the entries specify whether or in what order the action is to be performed. For the set of condition alternatives the entry corresponds to. Many decision tables include in their condition alternatives the don't care symbol or a hyphen. Using don't cares can simplify decision tables, especially when a given condition has little influence on the actions to be performed. In some cases, entire conditions thought to be important initially are found to be irrelevant when none of the conditions influence which actions are performed. To create the decision table, the developer must follow these 4 basic steps. Number 1 is identify all possible conditions to be addressed. Number 2 is to determine actions for all identified conditions. Number 3 is to calculate all the possible combinations of conditions. Number 4 is to fill the decision rules in the table. Entries in a decision table are filed either as yes or no, and action entries are generally marked as X. For the conditions that are immaterial, a hyphen is generally used for a put. The following is therefore a decision table demonstrating how decision tables can be used in determining whether to compute area or perimeter of a circle based on the size of the radius entered. So as usual, you begin with the title of the table. So this is a decision table on whether to compute area or perimeter of a circle. As you can see, this table contains the conditions and the rules and actions. An example is condition. If radius is less than 5, that is yes, then compute area as the action. If radius is equal to 5, then don't compute the area. Or, I repeat, condition. If radius is less than 5, compute perimeter. If it is not less than 5, then don't, or then, I repeat, if radius is not less than 5, meaning it is greater than 5, then compute area and display the area. If radius is equal to 5, then compute perimeter. And display the results. So in other words, my dear students and the rest of the learners, it is important to know how to make use of the decision table, the Y, the N, and the X characters. As you can see, it is only when a certain condition has been met that an action is taken under the actions section. If, for example, condition radius less than 5, we have Y for yes. And then straight away, we compute the perimeter. That's why we have an X here. Where there is no action to be taken, there is nothing which has been indicated in that cell under actions. Let's now look at data flow diagrams. A data flow diagram is a graphical representation of the flow of data through a process or sub-process that illustrates what happens to the data as it goes through the process, commencing from incoming data, outgoing data flow, stored data, and the various subprocesses the data moves through. Data flow diagram describes anything about how data flows through the system. Therefore, data flow diagram are visual maps that provides a clear understanding of how data moves within an information system. The two types of data flow diagrams are the logical data flow diagrams and the physical data flow diagrams. The logical data flow diagrams focus on the theoretical process of data movement through a system. It shows what information is moving, where it comes from, where it goes, and how it changes. It provides a clear understanding of system functionality and high-level data flows that helps in requirement analysis, user communication, and high-level system design. These DFDs are mostly used during the requirement analysis phase, the user communication, and high-level system design. The second is physical data flow diagrams. These focus on the practical process of information movement through a system. It shows how the system's hardware, software, files, employees, and the customers influence the flow of information. It provides a detailed view of how data is flowing and processed within the system's physical components. The physical data flow diagrams are used in detailed design phase, implementation planning, integration with the existing systems, and documentation, as well as maintenance. Data flow diagrams consist of 4 components, which are processes that represent systems functionality, external entities that represent the end users, the data store that represent database or data warehouse, and data flow that represent how data are flowing among these 3 components. The physical data flow diagrams are used in detailed design phase, implementation planning, integration with existing systems, as well as documentation and maintenance. And we are going to say that. And I have said again that it consists of 4 components. These are the processes, the external entities, the data store, and the data flow. Like a flowchart, a DFD also uses standard symbols and notations, which include the data flow symbol, the process symbol, the source and destination symbol, and the data store symbol. Let's now look at what we call the HIPPO diagrams. What's an HIPPO diagram? HIPPO stands for Hierarchical Input Process Output. It is a tool used to document and plan computer programs. It is a combination of a hierarchy chart and a set of input process output charts. The HIPPO diagram assesses the system and facilitates documentation. It organizes the software systems modules into a hierarchy. HIPPO diagrams can be used to get a high-level picture of the system's functions. The functions are further divided into sub-functions using HIPPO diagrams representing the system's functions. The HIPPO diagrams are excellent for documentation. By presenting the system's structure in a graphical format, designers and managers may quickly comprehend it. The hierarchy chart is a graphical representation of the program's control structure, while HIPPO charts describe the inputs, the outputs, and the functions of each module in the hierarchy chart. The HIPPO diagrams are therefore used to analyze systems, document systems, evaluate and refine designs, analyze systems, document systems, evaluate and refine designs. The HIPPO diagram assesses the system and facilitates documentation. It organizes the software systems modules into a hierarchy. The HIPPO diagrams can be used to get a high-level picture of the system's functions. The functions are further divided into sub-functions using HIPPO diagrams, demonstrating the system functions. The following is therefore an example of an HIPPO diagram. So that's how HIPPO diagrams look like, as you can see. So what are the factors that we need to consider? or what are the factors that can affect computer program design and analysis? What factors can affect computer program design and analysis? They include business requirements, software type and size, the development team, the development techniques and tools, development risks, scalability, the security, maintainability. We also have testability, as well as the clock speed. Let's now look at what we call the software design levels. Software design is a process to transform user requirements into some suitable form, which helps the programmer in software coding and implementation. The software design is the first step in system or in software design lifecycle, which moves the concentration from problem domain to solution domain. The design phase of software development deals with transforming the customer requirements as prescribed or as described in the SRS documents into a form implementable using a programming language. The software design process can be divided into the following 3 levels or phases of design, which are the architectural design, the high-level design, and the detailed design. So what do we have under the architectural design? The architectural design is the highest abstract version of the system. It is the specification of major components of a system, their responsibilities, properties, interfaces, and relationships and interactions between them. In architectural design, the overall structure of the system is chosen, but the internal details of major components are ignored. It identifies the software as a system with many components interacting with each other. At this level, the designers get the idea of a proposed solution domain. It defines the system's overall structure and components, such as the user interface, database, and reporting module. The architectural design uses tools like data flow diagrams and entity relation diagrams, or ERD. What about high-level design? The high-level design breaks the single entity multiple components concept of architectural design into less abstracted view of subsystems and the modules and depicts the interaction with each other. The high-level design focuses on how the system, along with all of its components, can be implemented in the form of modules. It recognizes modular structure of each subsystem and the relation and interaction among each other. While the detailed design is the specification of the internal elements of all major systems components, their properties, relationships, processing, and often the algorithm and the data structures. The detailed design deals with the implementation part of what is seen as a system and the subsystems in the previous 2 designs. It is more detailed towards modules and their implementations. It defines logical structure of each module and their interfaces to communicate with other modules. It involves converting the high-level design into a more detailed blueprint. This blueprint addresses specific algorithms, data structures, and interfaces. And with that, my dear students and the rest of the learners, we have come to the end of part 4 of 8 in the series. Let's meet in part 5 of the series, in which we are going to learn about program testing and debugging. Congratulations for learning part 4 of 8 on program design and analysis in fundamentals of developing computer program. You can access the rest of the parts in the series, as well as other computer or ICT videos, by clicking or tapping on Emeriswap ICT YouTube channel below this video. To subscribe to the channel, tap on subscribe button below this video in YouTube if it's not currently reading as subscribed. For any further correspondence, kindly write it to us through the email emeriswap@gmail.com. Thank you very much for listening to me. Let's meet in part 5 of the series, and God bless.